Good day, friends. How are you? Hope you all are well. Now, see, in our previous lecture, we studied about work energy theorem, right? Now, work energy theorem is very important. You know why? Because whatever work is there, now, is it up to the mark for the displacement of the body or not? So, this is what by which the energy conservation principle is involved, right? So ultimately this is all about energy conservation principle. Means, let's suppose if you have worked on somebody something, so whether the body got displaced or not, if the body got displaced up to a certain limit, so the work was done. But if the displacement was zero, means like in a circular path, if a body completes one rotation, so even if the distance was covered by the body but the displacement is zero, so that's the reason the work done was zero, right? So we discussed about the formula also of work done, like W is equal to F, which is applied force, and then the dot product with the displacement. Are you getting right? So now the other thing was the work done is equal to change in kinetic energy. Now why this terminology kinetic energy is there? It means there is an assumption that if you displace any body, so definitely you must have applied an external force which is done by an external agent, right? Now when it is displaced, so work is done, because the formula of work done that we have studied is applied force F, then the dot product with the displacement ds, right? So W is equal to F dot ds. Now at the time when you started applying the force, so at that time what was the initial velocity of the body, or was the body at rest? In both the two conditions it must be having a kinetic energy. Let's suppose if the body is having a initial velocity u1, right? Now the kinetic energy will be half m u1 square. Are you getting? Where m is the mass of the body, m is the mass of the body, right? Now let's suppose this was u1 and you have applied the force F, and due to which the body got displaced up to this distance, correct? Well, F is of course a vector quantity and this is the displacement vector, which is of course a vector quantity, right? Now this is the position, this is position, you can consider that position number 1, and this is the position number 2. Now this is the final position in which, let's suppose, the body is having velocity as u2. Are you getting? Now as the force is applied, so we have already studied that due to the force velocity gets changed, and that's the cause of acceleration. Are you getting? And this is interrelated, right? So this was the initial kinetic energy, Now let's suppose if we have to find out the final kinetic energy, KEF, the final kinetic energy, what will be that? Half m then u2 square. Is the point clear? Now the work energy theorem says, work energy theorem, WET, correct? It says that work done must be equal to change in kinetic energy. Now, whose kinetic energy is getting changed? Of course, the body. Are you getting? On which the work is done. Means, let's suppose this is the body, right? And this is a plane. Now, when the work is done and the body is getting displaced, are you getting? So, the mass of this body will be used while using the change in kinetic energy. Are you getting? This is the body. This was the initial condition of the body, right? And when the force is applied, right, so body got displaced and it came to this position. So this was the initial position and this was the final position. Are you getting? Now in both the two situations, we are assuming that the body is not coming to rest. Are you getting? So that's the reason we have considered that u1 is the initial velocity and u2 is the final velocity. Now, as per work energy theorem, work done is equal to change in kinetic energy. Means, change in kinetic energy means that can be represented as delta Ke. Now, delta Ke is nothing but kinetic energy final, right? Then minus kinetic energy initial. Are you getting? KEF and KEI. It represents the final kinetic energy minus initial kinetic energy. Now, which is equal to, of course, half m u2 square minus half m u1 square. Are you getting? And this is the work done, that is F dot ds. Right? So this is nothing but work energy theorem. Now this is very important at the time when you have to solve problems based on work energy theorem. You must know how to apply this concept. Are you getting? Now this can be understood very easily. How? Let's suppose if you work out on yourself. Are you getting? Now this is a little bit philosophical, but of course the philosophy is there. If you work out on somebody something, let's consider if you work out on yourself. So let's suppose initially your level is this. So definitely there will be some upliftment or displacement in your career. Are you getting? So this is as simple as it is. अगर आप पे काम किया जाएगा या आप अपने पे काम करोगे तो जाहिर सी बात है कि आप कुछ ना कुछ ऊंचाइयां जरूर छूओगे. आर यू गेटिंग? और ऊंचाइयां छूने का मतलब डिस्प्लेसमेंट. आर यू गेटिंग? अब जहां से स्टार्ट किया आपने वहीं पे अगर वापस पहुंच गए तो लोग क्या कहेंगे? लोग यही कहेंगे अरे आप तो फिर से जीरो से स्टार्ट हो गए. सो अल्टीमेटली फिजिक्स का जो रूल है वो सब जगह एप्लीकेबल है. यस और नो? नाउ व्हाट फिजिक्स सेज, लेट्स सपोज if the displacement becomes zero. Now how the displacement will become zero? It might be possible that either you were in rest and finally you were in rest. Are you getting? So ultimately the displacement may or may not be zero. How? Means you have started from this point. Now try to understand and try to look at this point. You have started your journey from this point, right? This was your initial point. Then finally you went up to here, then again went up to here, then again went up to here, then again you came here, and finally you reached to the same final point, which was nothing but your initial point. Are you getting? So the displacement was zero, but distance covered was not zero. Are you getting? Distance covered was this and this, right? But as per the presentation, as per the concept of work done, final work done must be zero due to the displacement becomes zero. I hope this point is clear. Now you just note it down, right? And then we will take a minor problem and we will solve it and just apply the concept and understand it well, right? Okay. So I'm going to rub it. You can pause the video and then you can note it down Are you getting? Just pause the video. Now see, we have another problem here, that let's consider that we have a small body of mass m is equal to 5 kg, correct? Now this is a tower whose height is given as 500 meter, right, as per the data given, correct? Now there is a small body of mass 5 kg which is dropped, right? Means you can consider like this. Now I am dropping it like this. Are you getting? Yes. So when it has been given in the problem that the small body of mass 5 kg is dropped from a tower whose height is 500 meter, so automatically the initial velocity must be 0, right? It has to be taken as 0, whether it has been given or not, because it has been written in the problem that the body is being dropped, right? Yeah. Now what do you have to find out? And at the time when it comes on the ground, so what will be the final velocity v at the time when the body hits the ground, right? This final velocity at the time when the body hits the ground has to be found. This one is clear? Now this particular problem can be solved in two ways. Either we can apply the equation of motion, else we can apply the work energy theorem, correct? Now work energy theorem means, first of all you need to understand which is the force, which force is acting on the body. Are you getting? If the gravity has been given, g is equal to 10 meter per second square, right? This is the gravitational acceleration. This point is clear? This is nothing but gravitational acceleration. It has been given as 10 meter per second square, right? Now what is the total energy? What is the total energy here, right? Now we can take a point, consider this point as A and consider this point, which is of course the ground, as B, right? The total energy at point A is total energy at point A, T, that is total energy. You can write it down. Total energy. You can consider it total mechanical energy, right? Mechanical energy. Now the formula of total mechanical energy is, generally we use that potential energy plus kinetic energy. Right? This is the general formula of total energy. Means the body must be having potential energy and kinetic energy, right? Now it may vary. Sometimes this kinetic energy may be lesser and potential energy may be higher. Then again potential energy may be higher and kinetic energy may be lesser, right? Now see, at this particular condition at point A, what is the total potential energy here? Now potential energy, the concept is m into g into h, right? And the kinetic energy is half m v square, right? Now at point A, if you see, as it has been given in the problem, the body is dropped. Dropped means initial velocity has to be considered as 0. So this particular segment, this particular term must be 0, right? Since U is equal to 0. It has been understood. Now we have only mgh part here, right? M has been given as 5, G has been given as 10, and H has been given as 500. Correct? Now this is the total mechanical energy at point A. Now what about the total mechanical energy? Total mechanical energy, that TE at point B. How much it is? Now if you see here, at the time when it just hits the ground, so it's having only the kinetic energy, not the potential energy. Why? Because slowly this height is getting reduced and finally it becomes 0. When it hits the ground, what's the value of H? The value of H is 0. So again we can write PE as potential energy plus KE as kinetic energy, right? So PE being mg and H plus KE half mv square, right? Now H is 0, that's the reason total this term PE, that is potential energy, must be 0 since H is equal to 0 at the ground. Right, this point is clear? Correct? Now we have conservation of energy principle. Now conservation of energy, this is COE, that is conservation of energy. Conservation of energy principle, right? What it says, that energy remains conserved throughout the journey, right? Means whatever total mechanical energy is at point A must be same at point P or any other point in between point A and B. This point is clear, right? Now let's apply. It means total mechanical energy TEA must be equal to TEB. This one is clear or not? Right? Means conservation of energy principle ये कहता है कि किसी भी पर्टिकुलर पॉइंट पे जब इसने अपनी जर्नी स्टार्ट की, किसने? ये स्मॉल बॉडी ने, किसी भी पर्टिकुलर पॉइंट पे ये टोटल मैकेनिकल एनर्जी हमेशा कंजर्व रहेगी, मींस सेव रहेगी, राइट? आपस में इनकी जो टर्मिनोलॉजीज है ये गड़बड़ सकती हैं, बट इनका एडिशन जो है वो सेम रहेगा किसी भी पॉइंट पे, राइट? दिस इज व्हाट कंजर्वेशन ऑफ एनर्जी प्रिंसिपल सेज. तो इसका मतलब ये हो सकता है कि व्हाट वी हैव टू डू, वी नीड टू इक्वेट द टोटल एनर्जी एट पॉइंट ए टू टोटल एनर्जी एट पॉइंट बी, right? So that's why we have written total mechanical energy at point A must be equal to total mechanical energy at point B. Correct? This one is clear. Now the total mechanical energy at point B is half mv square and the total mechanical energy at point A is 5 into 10 into 500. This one is clear? This point is clear or not, right? So you just equate it. Here m is known, v is unknown, and this is completely known. So we have one equation, one unknown. We can find out the value of v, which was the question, that find the velocity of this body at the time when it hits the ground. This one is clear. So let's do a minor calculation. What it will be? It will be a half mv square must be equal to 5 into 10 into 500, right? Again we can write it down. M, the value of m is 5, right? So 1 by 2 into 5 into v square is equal to 5 into 10 into 500. right? Now hence we can find out the value of V here, right? So V will be square root of 2 into 10 into 500, right? So then it will be again 10. So we will be having the value as as 100. Yes or no? Now check it. Let's do it. It will be here 2 5 are 10. We will be having 10 into 10 into 100. So 1 2 3 4. 10 raised to power 4 means we will be getting the value of this 100 meter per second. This point is clear, right? Now let's apply the work energy theorem in a different way. What we have studied so far. Now what the theorem says, that work done, which is basically F dot ds is equal to delta Ke, means change in kinetic energy, right? Now what is the initial kinetic energy? The initial kinetic energy is 0, right? What is the final kinetic energy? Half mv square. So we can mention it that Ke final minus Ke initial, right? This one is clear. Now Ke, what was Ke final? Ke final half, then m, then v square, and Ke initial was 0 since initial velocity u was 0, correct? So and F dot ds, what is the force? There is only single force, which is nothing but the gravitational pull on this body. What is that? This is m into g, right? And displacement. Now you look at here, the force F, which is of course F is equal to m into g. It is also in downward direction, and displacement is also in downward direction, right? So what is the formula? F into ds into cos 0, right? Now value of cos 0. What is the value of cos 0? Cos 0, the value will be 1, right? So that's the reason mg is the force F and ds is this height. So that's the reason we just mention it like this, mgh. So finally, what is the value of m? Again 5, then g, then 10, then h. H is 500, right? And this is what? Half, then m is 5, and then v square. So finally we got the same equation. Are you getting? So as I told you that work energy theorem is nothing but the application of conservation of energy principle. Are you getting? So the universal law is conservation of energy principle, right? So finally you will get the same value of velocity at the time body hits the ground. Okay, I hope you must have understood this. So it's okay for today. Then in the next topic we will be discussing more. Till then, bye bye, take care. Thanks a lot for watching. And if you haven't liked and subscribed my channel, you kindly like it and subscribe it. Thank you.